Alright, so this is part 2 of the logarithms video. I'm really comfortable with the first part, which in the first part I'm just going to show you how our students had no problem with using log, rewriting something in base 10, and then how one next step can be to show them natural log, and which really doesn't feel like a stretch for them. They've already established that as long as they're in the same base, life is good. So we'll just take a quick problem and go through that, and then I want to look at one property of logarithms. So here we go. Let's say 7 times 18 to the x plus 4 equals let's go 2 to the 9th. Sure. Okay, so students, this is the type of problem certainly when you start with students, even like if we're working base 10, they'd have a tendency to go, okay, I'm going to need the log of 7, I'm going to need the log of 18, I'm going to need the log of 2. Which it can be done that way, but we could certainly divide both sides by 7 to start. Right, so we have our 18 to the x plus 4 equals 2 to the 9th over 7. It's like, are those things in the same base? Well, no, they're not. And they could go through it and put it in base 10. They could rewrite 18 as 10 to a power. They could rewrite 2 to the 9th over 7 as 10 to some power. So I guess I'd make sure that they were comfortable doing that. But then, if you talked about, well, you said, okay, kids, we got the log key on our calculator. We also got this natural log thing. And that's a special tool, too. And you know how log deals with this 10, natural log deals with e. And there's obviously a lot of interesting stuff out there around e. I think for some of our students, though, it's tough for them to access, to read that literature, because a lot of it can be calculus based or based in statistics, and they're not at that point. One thing I tell my kiddos about e is, you can relate it to pi. It's kind of this phenomenon that just it shows up in mathematics, and it's really weird, but it keeps showing up. Some of my kids who really like music, you talk to them about, well, tell me about the major scale in music. Why is it the major scale? And the kids say, well, that's what sounds good. It just sounds good. It's like, well, E to mathematics can kind of be like the major scale to music. It sounds good. It just fits, and it fits in so many places. So you tell the kids E is a number. It's really special. And what the natural log does is it tells you the exponent. Tells you the exponent to put on E to get to your input, or to make your input. So like the natural log of 18 is approximately, grab my calculator, 2.890. So, you never want to lose sight of what does that mean. That means that e to the 2.890 is approximately 18. And this will be a messy one. That right-hand side, we had the 2 to the 9th over 7. But I'll put it in here, natural log, and obviously the kids need to be cognizant of how they're putting it into their calculator. Of 2 to the 9th over 7 is 4.292 approximately. So e to the 4.292 is approximately 2 to the 9th over 7. So, we've got a lot going on here. Let me copy this. Let's bring it down here. Okay, so the kids say, hey, bases are different on both sides. We can make them the same. We're going to work with the base of e. Might not make a lot of sense to us, but we know we've got a key in our calculator, function built in, that'll do it. So 18 is e to a power e to the 2.890. Let's see, and the exponent on the 18 was x plus 4, so our exponent here is going to be x plus 4, and that's equal to e to the about 4.292, and the exponent over there, oh, we didn't have one. I mean, if you think about it, its exponent was really 1. Awesome. So we've got the discussion of how do we combine those exponents. We've got one exponent over here, and it's not a stretch for kids at this point to say, well, that means that 2.890 times x plus 4 needs to equal 4.292. And you can do that same thing, that trick where you're like, oh, I don't have my calculator. What could we do? And the kids will just have you, write in natural log of 18 instead of 2.890. So it's a nice transition to, once again, working with exact answers. Alright, so I paused this thing because I had to go back and do each of these proofs once, but I didn't do them more than once. I wanted you to be able to kind of maybe see some misconceptions that I have or mistakes that I make. Maybe I won't make any. We'll see though. But here's the first one I wanna tackle. We got the log of a to the b equals b log a. And as I said previously, my hope was that approaching logarithms in this manner, how we did initially, would help build these properties. So we'll see how that goes. This first one, I just did a concrete example. Let's say let's look at the log of 5 to the 7th. Right? Log of 5 to the 7th. Well, fundamentally, log of 5 to the 7th, if you ask kids, well, what's that going to tell me? That's going to tell you that's equal to the exponent you put on 10 to make 5 to the 7th. Okay, that equals the exponent you put on 10 to make 5 to the 7th. So that is this thing in purple. Okay, that is the exponent I put on 10 to make 5 to the 7th. Okay. Now, 5 to the 7th can be rewritten. 5 to the 7th, maybe I should have picked a number smaller than 7, but here we go. 5 times 5 times 5, 4, 5, 6, 7. So that's 10. I'll try to work smarter, not harder. Okay, here we go. Maybe. Okay, we got it. So we're not there yet. I mean, I had to go back. Okay, what am I trying to prove? And I know we're not doing a formal proof because I did it here with 5 to the 7th, but I think there'll still be some power in it. Okay, so let's go back to where I started. Just a real quick, thought cloud. I'm trying to show that the log of 5 to the 7th equals 7 log 5. That's what I'm trying to get to. Okay. So 5, you got 7 of them over here. Is there another way to write 5? 5, each of these 5s, is 10 to the log of what? 5. 10 to the log 5 is 5. Right? Log 5 is the exponent you put on 10 to make 5. So I'm going to have 7 of those. Each of these 5s gets replaced with 10 log 5. So there's 2 of them. Okay, 3, 10 to the log 5, 4, 5, put one back here, 6, put another one back here, 7. Okay. So I'll use a highlighter here and clean this up so you can see where everything has gone. Okay, so this right here, that's still over here. Okay, the equal sign right here is sitting here. And all of these 5s have been replaced by these. Okay, cool. So we'll move down kind of the left-hand side of the equals. Nothing fancy is going to happen there, so let me just drop that down. Okay, now that equals, well, how many of these 10 to the log 5s do I have? I should have 7 of them. So 10 to the log 5 to the 7th. All right. All right. Now, hey, you said, how do you combine... So how do you combine those two exponents? Well, they would be multiplied. So 10 to the log 5 times 7 equals this, okay? And then we are there. Right, so the bases on each side are the same. So if left side equals the right side, then the exponents must be the same. And we have just said now log of 5 to the 7th equals, I'll just rearrange these over here. It's multiplication, so I got 7 log 5. Okay, the next property we were going to look at was we wanted to show that the log of a plus the log of b equals the log of a times b. Now, we've developed something with our students where if we made this statement here, students, a is equal 10 to the what? A equals 10 to the, we'd hope our students would say, log of a. I mean, that's the understanding we were trying to build when we started working with logarithms. And he said, okay, well, what's b equal to? 10 to the log b. Okay, well, he said, well, then what is a times b? Well, a times b is 10 to the log a times 10 to the log b. Cool. Which also can be rewritten as 10. I mean, if we gotta know some properties of exponents, right? I mean, same base here, and we're multiplying, then we want to add those two exponents. So that's all I'm gonna do. That's 10 to the log a plus log b. So really what I think is I'm going to look at right now is I have a times b equals this here. Now I say, well, what's another way to write a times b? Well, a times b is 10 to the what? 10 to the log of a times b. So 10 to the log a plus log b. We just copied that right side down. And we're sitting with the left side equals right side. Their bases are the same, so our exponents. Log of a times b equals log of a plus log of b.